Rhino Grasshopper is an amazing tool, easy to learn and hard to quit. I mean, it's sometimes as joyful and addictive as playing a game. With Rhino Grasshopper, you can set up as flexible AXISVM models as never before. I prove that you can achieve spectacular results in some days or weeks. Take a chance during the 90 days long free trial period available for every user. Combine it with our free plugin to extend your AXISVM modeling capabilities. Working on parametric models means also continuous learning. Beside the basic hundreds of components, nowadays there are 550 different applications available for Grasshopper, and 510 of them is free of charge. This means thousands of different components covering a significant part of the potential fields of usage. As architects, designers, managers, and many others can use Grasshopper in their projects, there are useful tools also for structural engineers. Parametric modeling gives space for your creativity, since there are a huge amount of correct solutions for each task. The solution you choose depends on your experience level, on the focus of the model you build, and on your future targets. First step is to start Rhinoceros 3D CAD software, simply called Rhino. To start Grasshopper, the user has 3+1 possibilities. First, on the Standard tab, click the Grasshopper icon. Second, use the Tools menu Grasshopper menu point. Third, start to type Grasshopper into the Rhino command line and press Enter, then Grasshopper starts. There's also a trick. If you go to File menu and Properties, among the general settings, you can set the Grasshopper command to be run every time Rhino starts. This is the most comfortable solution. Grasshopper is completely integrated into Rhino. It is a visual programming language to design algorithms that perform actions inside Rhino environment. At the top of the Grasshopper window, you find the menu bar. Below the menu bar, there are 11 component palettes by default, and the tabs of the applications installed by the user appear also here. Let's put some items from the Params tab to the canvas. Either drag and drop or click on the item, then click on the canvas works. Left-click on the subcategory opens a list including all the item icons and names in that subcategory. We have now a point, a curve, and a geometry parameter on the canvas. They can be easily aligned. Grasshopper provides two types of items, the parameters and the components. I talk first about the parameters. These items are simple and small. The purpose of them is to store data, volatile or persistent data. In other words, temporarily or permanently. Volatile data can come, for example, from Rhino. The Rhino window contains 4 viewports by default. User may enlarge them by clicking on the viewport name. The main sidebar offers the most important buttons to create geometries in Rhino. I create now a point, an ellipsoid, a closed polyline, and a curve. Look at the Grasshopper parameters. They have orange color. This means they are empty at the moment. Right-click on the point parameter, choose Select one point, click the point in Rhino. Then the color turns to gray, showing that the parameter contains some data. Let's do the same for the curve parameter. Notice that the geometry parameter can store many data types, point, line, curve, and so on, organized in a list. This example shows a significant piece of the power of Grasshopper, the flexibility. The implemented data handling and data conversions make Grasshopper highly user-friendly. If we click on an item, it becomes green. This is the color of the selected items. The data belonging to the item is highlighted with green in Rhino as well. Now I would like to move the objects stored in the geometry parameter in x direction. The distance between each of them is 10 mm, and I would like to create a series of 10, 20, 30, 40 mm as the magnitudes of the motions. I take the series component from the Sets tab. The components implement some functionality. They operate on data. The series component provides a list of numbers from 0 to 9 by default. User may see the output by hovering the mouse over the name of the component's output parameter. We can add new items to the canvas by double-clicking and typing the name of the component or the parameter we need. This is a panel. This is probably the most often used component in Grasshopper. At the top of the component pop-up menu, we can change or delete the displayed name of the selected item. Panel serves as text input field, and it is able to visualize texts or values. Let's configure the series component. You can follow the changes inside the panel. I create a number slider and connect it to the start input. Data transfer between the components happens via such wires. If we also change the step to 10, we get a series from 10 to 100. Reducing the count to 4, we have the required list. Notice that the single data are represented by simple wires. Data lists are represented by duplicated wires. I take now the Unit X component from the Vector tab, and I use the created series as input called factor to enlarge the unit vector. I create a move component with the Ctrl-Alt-Click combination. Grasshopper shows me where this component is located. I move the data of the geometry parameter with the scaled motion vectors, and the outcome is immediately displayed in Rhino. It is a balloon. Let's talk about the data structures of Grasshopper. There are data lists and data trees. Grasshopper operates on list level. I mean, the inputs of the move component are two lists that consist of four elements. The first geometry is shifted by 10 mm, the second is shifted by 20 mm, and so on. We can change the data list to a data tree by selecting the graphed option. This puts each list item into a single branch. The flow of a data tree is represented by a dotted line. The data tree is a list of lists. Therefore, each branch is combined with the complete list of the motions. All the motion vectors act on each geometries. If we graph the vector list, the combinations are clear again, and we have one single balloon. These operations put some zeros into the branch IDs that can be removed using the Simplify option. The flattening smoothes any kind of data tree into a list. In this example, it is equivalent by switching off the grafting. Let's see. There's another option called Reverse that reverts the order of the data inside a list. I can say inside each branch. In our case, this also destroys the balloon. We go back to the original state, and I show you one way to create multiple balloons. Using the linear array component from the Transform tab, the balloon geometry is copied, shifted, and pasted many times. With the count input parameter, we can specify how many copies we need. It always works to rename the number sliders, especially if there are many of them inside a script. Then we can publish them to the Remote Control panel. Opening the remote control panel, that is a great tool to control huge models, we see all the published sliders collected in a list. By moving the sliders, we can easily modify the numerical inputs of our model. Of course, the same can be done on the canvas as well. The user may switch off the preview of a component's output. Then the component turns to gray and the red previews disappear from the Rhino viewport. It is important to know that the geometry that is created with Grasshopper components is not a part of Rhino viewport. It cannot be edited unless it is baked into Rhino. The balloons are represented by black lines after baking. From now on, they can be selected and manipulated in Rhino, for example, moved with the aid of Gumball. At the same time, Grasshopper loses the control over them. The sliders do not affect the baked items anymore. I add a new component to the canvas called bifocals, very useful tool for beginners. It displays the name of each parameter and component. Let's save the script into a GH file, then save the baked and drawn objects of Rhino into a 3DM file. It is important to know that the contents of the parameters are not automatically stored in the Grasshopper script file. If I delete a referenced object from Rhino, the Grasshopper parameter gets empty. Now I undo the deletion. If I want to make my parameters independent from Rhino, I must select Internalize Data. This way we change from volatile to persistent data storage. After this action, I can delete the geometry from Rhino without losing the contents of the script. Then I save the data with Ctrl S. I open a new document. In the right upper corner, the user finds the File Browser control. The documents can be easily activated or closed by one click. In the next minutes, I show you some basic ideas to create geometry from the ground inside Grasshopper. I put the bifocals on the canvas, then add a construct point component that immediately creates a point in the origin of the coordinate system by default. I create another point by copying the component and connecting an input value to the x and y coordinates. To draw a line between these points, I use them as input of a line component. If the slider moves, the position of the second node and therefore the length of the line is changing. This may become a beam element in AXISVM. I may group the related components together in order to be able to move them together along the canvas. Not only a panel can contain text, but there is another item for this purpose called Scribble that can be found in the Params category, Utils subcategory. Double-clicking on the text brings up the editor, and we can create huge informative labels very quickly. Now I copy all components and press the middle mouse button to open a visual pop-up menu. I disable the selected components. When a component is disabled, Grasshopper Solver doesn't perform any calculation or evaluation on them. The components get a gray color that is slightly different from the color code of the preview of state. To create a rectangle, I remove the line component and take the rectangle from 2 points component from the same subcategory. As soon as the rectangle component is put on the canvas, we see its default preview in Rhino. Notice that it's independent from the points I created earlier, although the origin is coincident with one corner point. We must use the points as inputs in order to force the rectangle to be drawn on them. Such a rectangle may serve as the contour of a domain as an input of the AXISVM domain component. Let's mesh this rectangular region. In order to create a surface over the rectangle, we need to explode the rectangle. Thus, we get the lists of its lines and vertices. There are 5 vertices, because in case of closed polylines, the first point and the last point is the same. To make separate output for each vertex, I use the explode tree component and graphed the list of vertices into a tree. Zooming on the explode tree component, you can see small plus and minus signs. This means that the number of outputs can be configured by the user. In the end, each vertex has its own output and can be used as corners of a surface. The mesh surface component creates a regular mesh on the surface that can be easily configured. The display menu preview mesh edges function must be on in Grasshopper. I disable these components to show you another approach to create a rectangular shape. I need one point, and I'm going to apply the move transformation on the point. I need to move it in x and y direction, therefore I take the unit x and unit y vectors. The furthest corner is going to be created by moving along a vector that has both x and y component as well. The order of the points is important, therefore I connect the unit x first, then holding the shift button I connect the vector, then again holding the shift I connect the unit y. If I double-click on a wire, a small item called Relay appears. This helps to manage the wire positions. It is a useful tool to keep the scripts well organized. It's not able to store or manipulate the data, just lets through itself. Connecting a slider to the unit vectors allows to move the points smoothly. The geometry output of the move component contains the coordinates of the 3 translated points. Notice that the original point is not included in this list. Therefore, when I would like to create a polyline, I need to connect the original point and the translated points as well. To close the polyline, I take the Boolean toggle input and set it to true to connect the first and last points. Let's make this polyline dependent from a Rhino point. I create a point and make a reference to it inside a point parameter in Grasshopper. Holding the Ctrl and Shift buttons, I migrate the inputs from the construct point components to the point parameter. Thus, I am able to move the 2 wires together. From now on, the location of the square depends on the position of the Rhino point. To get the Rhino Grasshopper closer to you even after the webinar, I introduced some websites with useful information, courses and materials. The first website is rhino3d.com, the official website of the software. As I mentioned at the beginning, there is a 90 days long free trial period for every user. After that, you need to buy a license key. Full price is about €1,000 for a permanent license that never expires. I must mention here that the Grasshopper to AXISVM plugin works only on Windows operating system. Under the Learn menu, the user finds many video tutorials, courses, books collected from the Rhino Grasshopper community. A bunch of them are available for free. The official courses are gathered on the rhino3d.education webpage. I filtered to the English content, and as a first step, I offer 3 free classes. The Rhino 6 and 7 Introduction, the Pseudo Hopper 3D that helps to learn Grasshopper through playing, and the Fundamental of Grasshopper 3D by David Rutten. He's probably the most authentic person to learn from, since he is the developer of the Grasshopper environment. LearnGrasshopper.com is the website of Chris Voicelove. He works on BIM projects for Sweco company in Norway. He is civil engineer and participates, for example, in bridge design projects. He offers free webinar 2-3 times a year and offers some very useful documents. I recommend to download these files. They helped me a lot in learning and using Grasshopper. Chris is a member of the Beam Corner team, therefore his articles and videos are available on beamcorner.com, worth to check out. On this slide, I collected the links to the presented websites. At the top, you also find the link where you can register a Rhino account. This is required for starting Rhino, and you can use this if you download apps for Grasshopper. I mention here some paid courses as well. The next slide shows the more important canvas and component manipulations and some shortcuts. I do not go through this in details, it is handed over to you within some days after the webinar. In this section, I'm going to talk about the Grasshopper to AXISVM plugin. The first version was published in 2018. It provided practically two components, and it was able to transfer simple lines and members like beam elements into AXISVM. The next version, called V3.0, has already been able to send surface elements, domains, and set nodal supports in AXISVM. Then V4.2 brought some components for low definition as well. The material and cross-section library of AXISVM has become directly available from Grasshopper, linear static FE analysis can be started, and some settings have been available to speed up the data transfer in special cases. V5.0 is currently under development and it's going to be published in the first half of March. There are numerous new elements in the pipeline, special domains, beam end releases, eccentricity, rigid elements, and so on can be set. Low definition possibilities are further developed. Load panels, load groups, and load combinations can also be defined. The plugin is developed using the C# programming language in .NET 4.5 environment. It communicates with AXISVM via COM server, so-called API, Application Programming Interface. When we transfer data to AXISVM, hundreds of commands are executed in the background in a split of a second. The video illustrates what happens if we transfer some line elements and then some domains of a 4-story reinforced concrete building. In order to download the latest public version of the plugin, you need to visit foodforrhino.com. Here you can log in with your Rhino account to download apps. First, browse for AXISVM. Open the search results. Below the description of the plugin, you can find and download the available materials. After downloading the Grasshopper to AXISVM.gha file, go to your file browser. Right-click on the file and select Unblock. This is needed because the operating system sometimes blocks the downloaded files, but Rhino is not able to load a blocked GHA file. There are two ways to install a plugin. You either click the Grasshopper file menu, Special Folders, Components folder, or directly go to AppData, Roaming, Grasshopper, Libraries folder in the file browser. You see that I already have here the bifocals plugin. This can also be downloaded from the foodforrhino.com. Let's paste the downloaded GHA file into this folder. Then go to the local installation folder of AXISVM. If you have more versions installed, choose the one that you want to use together with Grasshopper. Copy the interop.axisvm.fw4.dll file to the clipboard and paste the copy beside the GHA file. Thus, the installation of the plugin is completed. To display the installed components, you need to restart Rhino. For detailed information about the components, you find the manual on foodforrhino.com. After restarting Rhino and Grasshopper, the AXISVM tab will appear at the component palettes. The components are grouped into 5 categories: inputs, params, elements, loads, and send. Input subcategory contains mostly value list components that provide drop-down menus filled with relevant data lists. These serve, for example, as input of a line, domain, or load definition. At the bottom of the list, there are the XYZ and XYZ components. These can collect, for example, the support stiffnesses, all load magnitudes in each direction. This way they serve as inputs for other components. For example, the distributed load definition for line elements requires the system and axis inputs. The icons appear if we hover the mouse over the name of the input parameters. The value list can also be added simply from the component pop-up menu, and they are immediately connected to the relevant input parameter. Go ahead to the most simple topic, the params subcategory. Let's take the cross-section parameter and cross-section component from the palettes. We need to double-click on the cross-section component icon to open the AXISVM cross-section library in a form. The cross-section parameter can optionally help to organize our script and collect the cross-sections into a list. If we compare the two panels, we see that the parameter doesn't manipulate the data. The components of the element subcategory contain functionality related to cross-section and material library, creation of nodes, line elements, surface elements, domains, supports, and some special items like edge hinge, spring, diaphragm, and so on. Practically, these components create the elements of the finite element model. Let's select a cross-section with the already known component. Then take a cross-section from text component. If I use the section name I previously selected and use it as an input, I find another cross-section table on the output side. The reason is that the cross-section library contains some cross-sections in separate tables but with the same name. In such cases, the cross-section from text component takes the first matching table. If I want to use the same table as above, I must add the CS table input as well. The third option to define a cross-section in Grasshopper is the usage of cross-section thick polygon component. It requires a closed polyline as input. Outer contour must have counterclockwise, and openings must have clockwise vertex order. We must give a name to the cross-section, and the cross-section process type may be selected. The thick cross-section will be added to the AXISVM model, but not to the cross-section library. Material component opens the material library form after double-click and stores the selected material. The material from text component works similar to the cross-section from text. If the given material name appears in more than one national design codes, the user must specify the national design code, otherwise the first occurrence is considered. Points or nodes can be created with a very simple component that requires just points as input. To define simple lines or line elements, we provide two components. The basic component has lines, material, cross-section, and line type inputs. It can transfer simple lines, trusses, beams, and ribs. The line extended component offers much more possibilities. Variable cross-section, local x-axis orientation, timber parameters, color settings, and so on. Here I show you a shortcut to make some magic. Alt and drag. It splits the canvas vertically. Tapping Alt again would change to horizontal split. It helps to gain some free space on the canvas if everything is full. To define beam end releases, the user needs to define a beam end release by selecting the release type and setting the release function index if necessary. Then, connect it to the appropriate degrees of freedom. The prepared AXISVM releases serve as start release and end release input for the line extended component. Line eccentricity component provides a wide range of eccentricity settings. including the eccentricity releases as well that become available in X6R2 edition. These components are located in the second group of the elements subcategory. The following item we check is the mesh component. This has 5 inputs. The very first input, called meshes, is always required. This component is able to transfer Rhino mesh to AXISVM as edges, surface elements, or domains, depending on its connection with the sender component. Therefore, the other inputs are not always relevant. For example, an edge or line element needs rather cross-section than thickness, and a domain will not consider any line type, of course. If we want to define domains, there are many other components available. There is a basic domain component. The contour, the element type, thickness, material, holes, and color settings can be given. The thickness and eccentricity of the domain can be either constant or variable. Variable thickness settings have a separate component. Constant thickness can be defined connecting a single value. Eccentricity setting is implemented with the same logic. Furthermore, we offer components for 6 special domains as well. Composite rib domain, domain with custom stiffness matrix, hollow core domain, ribbed, trapezoid, and XLAM domain setup is available. Each of them gathers the specific inputs like profile sizes, hole type and direction, rib eccentricity settings, XLAM parameters, and so on. Go on to the next group. There is a supports component that collects the nodal, line, and surface supports from the script. Then, the supports component will be connected to the sender component in the end. There are the 2 last groups in this subcategory. Diaphragm, edge hinge, and rigid elements are in the first group. Gap and spring elements are in the second. It is important that the AXISVM line component is not able to set up spring and gap elements because it doesn't get the required inputs. These element types can be created only with these special components you see now on the screen. We finished the elements subcategory and go on to the loads. I take first the load cases component. It is implemented the same way as the supports component is. I mean, it is a collector component of load definitions, then it will be connected to the sender component. The first input is the load case name. It is ST1 by default, but it can be changed, and then a new load case is created with the user-defined name in the AXISVM model. The load cases can be assigned to load groups and can be a part of load combinations considering user-defined factors as well. The nodal load component expects an AXISVM point as input. Note that Rhino point is not accepted because that's not able to have an AXISVM ID. At least one force or moment component must be non-zero in order to create a new nodal load. The distributed line load can be prepared with a basic and an extended component. The basic configuration is able to create a distributed force load in the chosen direction over a given section of the line element. The extended component can manage every force and moment components together, and trapezoid or rectangular load profile can also be created with it. Domain concentrated load. It expects the force and moment input via XYZ components. If one single value is connected instead of XYZ component, then all the 3 force components will be equal to that value. The distributed surface load is used for surface elements. It accepts AXISVM mesh input, nothing else. Next one is a distributed domain load component that can be used to define a distributed load over a complete domain in one selected direction with a given constant intensity. The domain area load component is the complex variant of this. It can apply the load either over the complete domain or just over a closed polyline inside the domain. 3 reference points can be given in order to consider a linear distribution. But if the point 1, 2, 3 input is empty, the intensities do not represent a linear distribution anymore, but they are applied in x, y, and z direction. The domain polyline load is dedicated to set up loads along a polyline in the domain. Every force and moment component can be defined for the start and end point of the polyline. There is a component to create load panels from line elements, surface elements, or domains. Concentrated load, distributed load, and polyline load can be applied on these load panels. Self-weight component has 3 XMesh inputs that will be renamed in the released plugin. These inputs distinguish between mesh edge, surface, and domain. Thermal load may be applied on line element, mesh, or domain. For line element, the direction of temperature variation must also be selected from amongst local Y and Z axis. We reached the last subcategory. This contains 2 components, settings and Grasshopper to AXISVM, also called sender component. The settings is the first mandatory input of the sender component. To open a completely new AXISVM window, we need to set the new input to true. To open an existing AXS file, the new input must be false, and the file path needs to get a valid input. AXISVM windows need to be closed always by the user, since the models may be wanted to be edited after closing the Grasshopper script. During data transfer, the default process is to clean up the AXISVM model and resend all the data after any change. In case of complex models, this might be time-consuming. Therefore, the settings component offers some options for special cases to support the user. Just point coordinates can be used to speed up the data transfer to AXISVM if just the node coordinates change and the relations and properties remain all the same. Send-only properties function is valuable if we have a huge model and the geometry remains unchanged, but we need to update thickness, line type, release type, or other properties of the elements that have no influence on the geometry itself. There are 3 more useful options that can be activated on demand by setting them to true. Check double removes the duplicated nodes and lines if there's any in the model. Intersect lines activates the intersect functionality of AXISVM if it's not automatically on. The last option is to decide whether we would like to start a linear static finite element analysis on the transferred model. Sender component collects all types of elements and loads that can be transferred, from points to load cases. The items that are not connected to the sender component will not be transferred to AXISVM. The sender component has one output called error. We need to connect a panel in order to display the error messages in case they occur. For example, if I use the AXISVM line component, it sends simple lines by default. When I set the line type to truss, it immediately sends error messages because material and cross-section input is missing. Therefore, the trussed element type cannot be set. In the last section of the webinar, I show you how to transfer a cell phone tower model into AXISVM. This is a typical example where the Grasshopper script is a powerful tool for structural engineers. Setting some dimensions as parameters and figuring out an algorithm for cross-section assignment, more customers can be easily satisfied quickly on the basis of the same Grasshopper script. The tower consists of two types of segments, and I'm going to consider the self-weight and some wind load in separate load cases. The parameters I chose are the segment height and count in the parallel and in the conical sections, the base width, and the width of the parallel section. At some angle, the diagonal beams of segment type number 1 would be too long and weak. Therefore, the segment type is automatically changed from type number 1 to type number 2 at a given limit. The following considerations have been done during modeling. The grid is continuous in the consecutive segments, thus the diagonal beams meet in a common node. The beams must be grouped for cross-section assignment and to set beam end releases. I am not going to show you how the geometry is created, because there are many different good solutions. I can decide whether I create the parametric segment and I distribute it, or I build the model in a way that I have immediately the required beam groups. Do I create the geometry inside Grasshopper, or I draw it in Rhino, then scale, shift and rotate it? Decisions have to be made based on the aim of the modeling and personal preference and experience. Last but not least, the algorithm for cross-section assignment needs to be figured out. I made some simplifications compared to the reference model I had. I used 11 cross-sections in the model. I decided to split the tower to A, B, C, D, E, F sections, and I defined the assignment separately for each section, for each beam. As going along the tower upwards, the beam cross-sections are smaller and smaller. Take a short look at the Grasshopper script. It starts with many number sliders as inputs. Then the points of the tower legs are generated. The angle of the diagonal beams is calculated for each segment in order to find the location where the segment type needs to be changed. In the end, the segments are grouped into list A and B based on the required segment type. Then the beams of each segment are created. Here you can see a point parameter, which collects every single point of the tower. Except of the tower legs, every beam needs beam end releases. Therefore, the beams are collected into two groups. The endpoint component creates a data tree from separate inputs, using them as branches. The indices of the endpoint component grow from 0 to 10 in order to easily match the 11 different cross-sections I use in the model. First of all, I generate and fill the 11 cross-section components based on the list in the panel. When it is finished, I collect the cross-sections with the aid of two cross-section parameters. The first group contains cross-sections from 0 to 5, the second group from 5 to 10. Yes, cross-section number 5 is used in both groups. I cross-check the data in panels. It is time to start a new AXISVM model. I reorganized the windows to show Rhino, Grasshopper and AXISVM parallel. Let's transfer first the tower legs to AXISVM. I put an AXISVM line component onto the canvas and connect the appropriate lines as an input. Notice that this doesn't send anything to AXISVM because it is not connected to the sender component. Then I select the material and connect the second cross-section group. I take the line type value list and select beam. Notice that the line's input is a data tree. The cross-section input is a data list. We can visualize this with Param Viewer components. Our target is to assign different cross-sections to each line group, or more accurately, to each branch. With the current settings, the complete cross-section list is assigned to each branch of the line input. This is not what we want. We need to graft the cross-section list to achieve that Grasshopper pairs the line branches with the cross-section branches as we want. I apply the graft option rather on the input of the line component. The outcome is the same, just I could not visualize the details here as good as I did at the cross-section parameter. Now we have 6 AXISVM lines, and we can connect them to the sender component. As soon as we do so, we see that only one branch of the data tree is visualized in AXISVM. The sender component can handle only data lists until we have one single settings component connected. If we would have 6 AXISVM windows open, each branch of the data tree would appear in separate AXISVM windows. We want to put everything into one window, therefore we need to flatten the AXISVM line input into a list, and then each tower leg appears as expected. I make some space on the canvas because to send the released beams, I need to use the line extended component. I connect the lines input, select the line type, set the material. I want to use the same cross-section along the beams, therefore it is sufficient to feed the cross-section start input, and the cross-section end is considered to be the same. The cross-section input needs to be grafted for the same reasons I explained earlier. I take the beam end release component and set the release type to hinged. Function index is not required for this release type. I set rotational releases about the local Y and Z direction of the beams and connect the releases to the start release and end release inputs of the line extended component. The data can be quickly sent to AXISVM, and you can see that the beam end releases are set as expected. To keep the script clear, I connect the lines into a parameter first, and I lead them to the sender component and then to the self-weight component from there. The output of the self-weight component must be flattened into a list because we would like to consider every piece of that within one common load case. I take a load case component, give it a name, and connect the self-weight load into it. After making a wire towards the sender component, the new load case is generated in the model. The nodal supports and the wind load are still missing. To create them, I go to the point parameter that collects all the points of the tower. I connect it to an AXISVM point component. The nodal supports need to be applied at the bottom of the tower. Those nodes are available in branch 0 of the data tree. Using the split tree component and mask 0, it is possible to separate the nodes we need from the rest. The output called positive contains the 3 nodes of branch 0 as required. Next step is to connect these nodes into a nodal support component and set a high stiffness value to each degrees of freedom. Look that instead of an XYZ, XXYYZZ component, I connected one single value, and this is applied automatically for each degrees of freedom. The nodal support components lead to a support component, and then we go to the sender component. We need to recognize that the nodal supports have not appeared in the AXISVM model yet. The reason of this is that the points are not connected to the AXISVM sender component, therefore the supports component doesn't know which node indices to refer to. After connecting the points to the sender component, we still need to flatten the data tree in order to transfer all the data and the nodal supports finally visualize in the model. As a dummy wind load profile, I created a parabolic distribution inside the Grasshopper component that allows many kind of function manipulations and sampling. I create nodal loads in x direction. If I simply connect the data tree of points and the data list of force magnitudes, all force magnitude is applied on every single node. To change this, I graphed the data list of forces. This way, each branch of the data trees are paired, and I have the required force magnitude at each level of the tower. I need to create a load case, give it a name, and flatten the nodal loads to a list. Then connect it to the sender component. And the new load case is available in the model. I would like to highlight that although more than one inputs are connected there, the load case's input doesn't need flattening in this case, because the two single inputs are organized into a list and not to a data tree. To summarize the main steps of the process, here's a list for you. We need to open AXISVM, define all important properties of the line elements, in this case, material, cross-section, beam and releases. Nodal supports need to be set up, and nodes need to be transferred as well. The loads must be applied within load cases. I presented the usage of the self-weight and nodal load components. Last option in the list is to start a linear static FE analysis. First, I'm going to activate the intersect lines options because at the segment type number 2, there is one intersection that is not implemented in the Grasshopper script yet. Then run analysis must be also true. I need to save the model, then the analysis runs through. Automatic optimization is not yet available from Grasshopper, but after the completion of an analysis, the user can visualize, evaluate, and process the results and may start further simulations. Today you learned the basics of a software that is more and more often used by engineers because inside Grasshopper anyone is able to implement algorithms and parametrization without having to learn any programming language. The flexibility of Grasshopper makes feasible to model even the most complex shapes with moderate effort. The engineers may need some creativity and courage at the beginning to choose a repetitive task in which they could really try to involve Grasshopper. If they find a potential application with well-chosen parameters and clever modeling that keeps the model cohesive, they can spare a lot of time in the future by reusing the scripts in upcoming similar projects. I guess so that based on the webinar, you will manage to use the components of the Grasshopper to AXISVM plugin. The components require more or less the same inputs as the AXISVM user interface forms, so probably most of them will be clear for you. I hope you enjoyed the presentation, and you can hardly wait to download Rhino and our plugin to try yourself in parametric modeling. Thank you for your attention.